Good evening, everyone. Welcome to the fourth video of the IB to IIT Transition series. So, for the past three videos, we were able to solve some problems. So, three problems were solved. The first problem was on something like you have an Earth and you have a satellite which are seen to be revolving around it. Okay, typical Kepler's law problems. And then, if the potential energy or the potential of the Earth increases by a factor, and that too, if it is a repulsive potential, then what can happen? And how does it affect the time period? That's what is the first problem. So I showed you about, okay, what is that you need to work on this. Then the second problem was something like you have a coil of wire. You had a coil of wire and an electric current was meant to pass through it. And as a result of this, if it is kept in an external magnetic field, then this coil of wire used to get tilted like this, right? So why did it get tilted? So therefore, for example, if this was a coil of wire, just kept like this, and passing an electric current like this, it got tilted like this. So you are interested to find out what was the torque which has been exerted onto it. So what is the angle between the area and the vertical? That was the question. So this also we did this. So part of this was a bit of out of syllabus as compared to IBDP, and I had taught you about how to work on such kinds of problems also. Right. Okay. The next thing that we looked at, that is the third problem, was something related to a tennis ball which was kept inside a container and of containing water, and then we made it to completely sink into it, and the moment I left my hand it started going upwards, and to find out what was the velocity, what was the viscous force, Stokes formula, and so on. So all this were within the syllabus. We also did try to relate or to get an expression for this. This was about the conservation of energy. Okay, so as we have observed from all the three problems, most of the time the problems are within the syllabus itself. But only thing is the level of depth would be a little bit higher. So you need to think a lot and then try to approach it. Anyway, thinking is not new for IBDP students. Critical thinking is something which has been imbibed in your curriculum. So as a result of it, if you are able to solve problems related to IBDP, that to structured problems, then definitely these kinds of problems should not be very difficult. You should be able to do it. Nevertheless, you have that phobia thinking that I will not be able to solve IITs. IITs will be very tough and so on. So let us not keep that in mind and let us try solving such kinds of problems. Who knows, one day you will also be able to clear an IIT exam. Okay, now without wasting your time, let me move on to the next problem today which we are discussing. Just give me a moment, I will share my screen. Okay, now let us begin. So here the question is about a hydrogen ion is accelerated through rest from rest through 192 volts and enters a magnetic field of 0.1 Tesla directed into the page. Its velocity is perpendicular to the field. So you have an hydrogen atom which is coming like this, and then it comes like this over here. It's a hydrogen ion, which means what? So every phrase here is very important. So hydrogen ion means its charge is Q is equal to plus 1e. Okay, because one electron is ripped off, and then its velocity is perpendicular to the field. Find its speed as it enters the field. Very simple problem, right? You would have done these kinds of problems already. So how do you do? It's nothing but you have the formula which gives you R is equal to mv divided by qb, and based on it you will get the value of v. Okay, or maybe is radius given? No, radius is not given. So you will not be able to do this one. Okay, this you can use it for this one here. Okay, so this we need to find. Let me tell you how to do with this. So if it travels exactly 1/4 of a circle before exiting, how far below its original path does it come out? Okay, so how far below its original path? Okay, let us address one by one. Let me go to the next slide. Okay, let me change my pen color. Okay, a hydrogen ion is okay. Now find its speed as it enters the field. So let me first draw the diagram to understand what is happening over here. So you have magnetic field like this. You have magnetic field like this. And let me assume there's a positive ion, a hydrogen ion is now transiting it like this. It goes like this. And then it says If it travels exactly 1/4 of a circle, what is 1/4? Now it forms like this and it goes down like this. Okay, so if I fold this full one, it's one full circle. So, but it's not going like that. It's exiting out of the magnetic field at this point. It's coming out like this over here. Okay, so the moment you draw the diagram, you come to know, okay, what is the third question? See, if it travels exactly 1/4 of a circle before exiting, how far below its original path does it come out? What is this distance? What is this distance? This distance, because if this is the center, this should be your radius, right? This should be your radius. So therefore, if you find the radius here, you have an answer for this and you have an answer for this one. See, this is not an IIT problem. This is nothing but a problem which I have made so that it becomes easy for you, okay, to understand the IIT problem. Okay, it's nothing but your level 1 IBDP problem. Such kinds of problems are already being done in the class, so you will be able to easily solve this. Okay, so therefore, now the formula that I had written already in the previous slide is, it tells you R is equal to mv divided by qb. Now what is known? Hydrogen ion, mass of the ion should be known to you. Velocity is unknown, it's not given over here, which we need to find, which comes from here, zigzag rule, right? So you'll be able to find out from here. Charge of an hydrogen ion, you know, which is 1.6 into 10 power minus 19. Magnetic field 0.1 Tesla. Okay, if you know this velocity, if you are able to answer the first question, next question you are able to answer it clearly. Now how do you answer the first question? That's the question over here. So what we do is, so as the particle comes over here, so what will be the energy in this? The energy would be equal to half mv square. So which will be equal to half mv square will now be equal to, why does it get the energy? Because it is getting accelerated by the electric field over here. What is the electric field? 192 volts. So the work done here should be equal to the kinetic energy, which should now be equal to Q into V. What is this V? V is the potential difference by 192 volt. Okay, maybe they would have put a battery over here, or maybe some electric field is over here. So it is now getting accelerated. So as a result of it, the work done by the charge is given by Q times V. Okay, we get this here. So from here, we can find out what is the velocity. We can write V square is equal to 2 times Q into V divided by M. Now let us substitute all the values over here. 2 multiplied by 1.6 into 10 to the power of minus 19 multiplied by 192 divided by mass, which is 1.67 into 10 to the power of minus 27. Okay, when I do all this and take the square root of this one here, 368 multiplied by, here it is minus 19, here it is minus 27. This should be, when it comes upwards, it will be 10 power plus 8 over here. 10 power plus 8 whole to the power of half square root, which should now be, if I take the square root once again over here, this should be 19.18 into 10 power 8 is 10 power 4 square root. So which is nearly equivalent to 1.98 into 10 to the power of 3 meter per second, which is, I made a mistake here. See, 19.18 into 10 power 4 should have been 1.98 into 10 power 5 here. So this is wrong. It will be 2 into 10 to the power of 5 meter per second. So as a result of this, this becomes 2 into 10 power 5. When I do this, this becomes 2 point, so minus 27 plus 5 is minus 22, minus 22 plus 20 should be minus 2 here, minus 2. So this now becomes 2 centimeter. Okay, so therefore radius equal to 2 centimeter, it will be below 2 centimeter. That's what we can say. Okay, now let me move on to the next one. So first question was quite easier, so it was not at all difficult. One can easily do it. Next question. Now I'm just continuing this one because it should facilitate the next question. So I'm just doing this one, but this is a little bit higher. Okay, so you generally don't do these kinds of problems in IB. So as a result of it, I said it's a level 2 problem. The same setup is now used with the singly charged positive ion of mass M. Now instead of using a hydrogen ion, I'm going to use a different ion which has a mass number A. Okay, and show that the quarter circle radius the vertical drop becomes R is equal to so much. Take A equal to 144, 196. If A can range from 1 to 196, determine the minimum detector height and the minimum horizontal width of the field needed so that every ion completes its quarter circle before hitting the screen. Now it's a little bit higher over here. Now what does it do? So it does like this. Okay, so now what you do is, it says, it again describes a quarter circle. Okay, and it says about the height of the detector. Okay, when it says about the height of the detector, then what we do is, maybe can we consider it like this? I will consider the magnetic field like this. I will consider the magnetic field like this. And I will consider charge to go like this over here. This charge to go like this. So it completes 1/2 of the path, 1/4 of the path, and you keep the detector here. Now, if you see, if the detector is kept here, then what can happen? Do you think the charge will come and hit here? Charge will not come and hit here. So there's no point. So I should definitely raise my height of the detector until here. Okay, so it comes and hits. But there's also a possibility, okay, that some charges might hit here and some charges might hit here. Okay, so within this range it can hit. Now, why am I putting this range? Because there was a question asked in the previous one. It told you that, okay, determine the height of the detector height and the minimum horizontal width of the field needed so every ion completes its quarter circle before hitting the screen. Okay, so therefore you want all the ions which have a mixture of ions starting from 1 to 196. There it was only one hydrogen ion. Now I have taken many such ions. Okay, one of them could be having a mass number 1, second one could have a charge mass number of 2, 25, 37, 48, 56, whatever it is until 196, whatever is the mass number, all of them should come and hit it. That's the question. Now, why should it depend on mass number? If you ask me this question, then the question is answered over here. It tells you that the radius of this path depends upon the mass number by this formula, which you need to prove it. Now, first thing is we need to prove this and then we need to come to this question. Okay, now let us start proving this. Now, how do we do this once again? So, we need the quarter circle radius. In the previous problem also we have solved the radius. Here also we are going to get the radius. Now, how are we going to do this? We are going to start with something like half mv square is equal to q times v. This is the first thing that we are going to do. Okay, because you see there's a v here and then from here only we are going to do it. So we are getting v should be equal to 2q into v divided by m. We have got the first equation. This is v, not theta, small v. Next, what's the next thing? Now we know that the radius of the circle is given by radius r is equal to mv divided by qb. Okay, now what is this m? M is the mass of the ion. What we will do is we will not put this mass of the ion initially, okay, which is nothing but m times u here. What is this m? What is this a? What is this m here? See, if I take only one hydrogen ion, this mass is m. If I take a nucleus which is a much larger one, this can have a such m over here, right? Several protons. See, one hydrogen ion is nothing but one proton. Okay, so therefore, if I take several such ions, this one big nucleus, right? So you have one big nucleus over here, okay, and not only protons will have neutrons and so on, but he is very clearly saying that's once again a singly charged positive ion of mass m, which means what? It has only one proton over here, while there are several neutrons over here. Okay, it's a hypothetical thing. Okay, it says only one proton and several neutrons. The mass of this nucleus that you consider will have a large number of the neutrons, but it will have only one proton, only one charge over here. Okay, that's what it tells you. So which means that you are not going to change the value of q. You are going to change only the value of m over here. Okay, so you have got r equal to mv by qb. Now we will substitute this value here, because what do we need? We only need this value of r, right? We'll substitute this value and we'll write m into, what is this v here? V is not potential, v is velocity. I'll substitute this as this v square here, right? So this v here should have been square root of this into square root of 2qv divided by qb, and there's a qb here. Sorry, 2qv divided by m, not qb, divided by m divided by qb. I'll write like this over here. So when I do this, what do I get here? See, now if you look at this expression, everything is inside only. Okay, nothing is outside. So I will pull everything inside only. Okay, so that nothing is outside over here. So I will now write this as equal to square root of this m. When it comes inside, what will happen? This will become 2m square multiplied by qv divided by this m here. This qb is also inside, which means what? I'll write this m as usual, and this qb, when it comes inside, it becomes a q square into b square. Okay, so you should sometimes you go from answer to question only, right? So therefore this m and this square goes away, this q and this q square goes away here. So what do I get over here? We get this answer as 2m then you don't have a Q here, you only have a V here. I'll rewrite this Q. So you have M here, you have V here. Which V is this? Not velocity, it is potential difference, capital V, divided by this square is extending. Okay, the square root is extending, divided by, you have a Q here and you have a B here. You have a B square here, Q B square over here. Now, how is this expression different from here? Say denominator QB square is here, this V numerator here, this 2 is here. What is the difference over here? A times MU, right? But what is this M here? The mass of the bigger ion, which is equal to A times MU, right? The MU is the mass of one nucleon. So what I'm going to show is, I'm just going to write that the mass of the nucleon can be written as MU times A. And then I'm going to write R is equal to square root of 2MU A V divided by Q B square. Now, have we done this or not? Okay, so this should be very easy in that case, right? We already got the value here. Okay, so thus we have proved this expression also. Now, what's the next thing? The next thing is about take A equal to 144, A equal to 196, find R for each. So what you should do, you should substitute all the values over here. So how do I substitute? First, let me take for 144. Let me first find out. See, this is A here. If I put for hydrogen ion first, if I put A equal to 1 for hydrogen ion, how much do I get? I get R is equal to square root of 2MU V divided by Q B square, which I have already shown you in the previous expression. Where is the previous expression? It's here. It's here, we already done here, right? What was the radius here? See, I did the same thing. In fact, I did not get the general expression into it, but instead what I did was, I just did it separately part by part and finally got the answer. The radius of this circle, which it was showing here, was seen to be 2 centimeter over here, right? So therefore, what I will do is I'll take this as equal to 2 centimeter. Okay, now if A equal to 1. Now what is he asking? If I put A equal to 144, where is this A coming? A is inside this over here, right? So if I take this 144 here, outside the square root, what will happen? It will become 12 over here, right? So therefore, we'll get R for 144, this for R for 1 here. 144 will now be equal to 12 times R1, right? If I put 144 here, this will become 144 into whatever is there inside this quantity. And then 144, square root of 144 is 12. 12 times whatever is there inside this. And this value we already know, this 2 centimeter, which should be 12 into R1 should be equal to 24 centimeter. Now in a similar way, let us do it for R196 also. Okay, I'll do it here. R196. 196, what's the root of 196 over here? I'm just going to replace this. 196 is nothing but R of 196. 196 square root is nothing but 14. So therefore, 14 multiplied by 2 centimeter should now be equal to 28 centimeter. 28 centimeter. Okay, so 2 questions we have already answered over here. Okay, so 2 parts we have done. Find R for each. Okay, the major thing is that we need to prove this one. So this we have already done. Next, if A can range from 1 to 196, determine the minimum detector height and the minimum horizontal width of the field needed so that every ion completes its quarter circle before hitting the screen. So what do we have? We have, this is your magnetic field, and then this is a magnetic field. A charge plus Q was seen to be moving like this. It moved here, describe a circle here, and you kept a detector here. If the detector was kept here, it would not register the charge, right? Since it has to come until here, so you need to keep the detector until here, right? So therefore, so what is the height of the detector as you measure from here? Okay, so this height should now be equal to, how much is it? This height should have been equal to the radius of the circle. What is the radius of the circle? Let us determine what is the radius of the circle here. What is that? We got 28 centimeter, 196 to 28 centimeter, right? Okay, so therefore, if this length is equal to 196 centimeter, definitely this charge will come and hit over here. Okay, if there is a this is a nucleus, okay, which is having a, let us say, a 190 over here, then where will it hit? This will come here, it will hit here over here. Let us say, where does R equal to 1 hit here? That is your Q equal to 1, that is your mass number equal to 1. This might hit here, the hydrogen nucleate might hit over here, right? And where does your, let us say, for example, which one? I'll take something else. Let us say 25 or 30 will hit, 25 or 30 might be hit over here, right? So therefore, any nucleus starting from 1 to 196, all of them will definitely be registered in the detector if the detector's height is seen to be not 196. It's seen to be how much? Seen to be the radius of the circle. What is the radius of circle? I wrote it wrongly. 28 centimeter. If the radius is seen to be 28 centimeter, definitely it will go and hit there. Okay, so therefore we have got the minimum height of the detector. This should be equal to 28 centimeter. Minimum horizontal width, which means what? Let us say, for example, if the magnetic field truncates here itself, then what will happen? So the moment it goes over here, it tries to go like this over here, right? There's no bending, right? So if there is no bending and if there's no magnetic field, there's no magnetic force, automatically the charge will now go tangential to the path. So what you should do? So the magnetic field should act in such a way until it comes nearby to the detector. Okay, there should be a magnetic field. So therefore, magnetic field width should be this length over here. How much is this? Once again, radius, which should be equal to 28 centimeter. Thus, the height of the detector should be equal to 28 centimeter. Radius should also be equal to 28 centimeter. Only then you would be able to see that the charges will cross that magnetic field region and go and hit the detector. Now, I hope this is clear about how much amount of thinking and what is that you need to look into it. Okay, so fine. Now let me move on to the next one. Now we have done 2 levels. Level 1 was quite easier. You need not even to have to visualize so much. It is quite easier. Level 2, you really need to visualize a lot. What do you learn from here? It is not only doing mathematics, but also doing mathematics and then understanding the problem becomes very, very important. And without that, you will not be able to solve any problem over here. So that's where we say critical thinking is essential. Logical reasoning becomes very, very essential. Okay, you should be able to visualize the problem. Next, now let us look at the actual problem over here. So actual problem is also very similar. A positive singly ionized atom of mass. Let me change my pen. Okay, mass number EM, very similar to it. That means what? It's not a hydrogen atom. So this is having EM times A. Okay, where M is the mass of the hydrogen ion. It's accelerated from the voltage 192 volt. We have used the same voltage. Thereafter, it enters a region of width W with a magnetic field B0 equal to 0.1 K cap Tesla. That is along the Z axis. See, this is your Z axis. Okay, positive Z axis, that means magnetic field is pointing towards me. Away from, sorry, it's coming out from the panel, right? The ion finally hits a detector at the distance X below its starting trajectory. It comes and hits over here. So this ion comes and hits like this over here. Earlier, what was the problem? Earlier, the problem was detector was somewhere over here. It used to complete only 1/4 of a circle. Here, what's happening? 1/2 of a circle. It's completing. Okay, next. Which of the following options are correct? What is this problem one? It's only a true or false problem. It is hardly only for 3 marks over here. And definitely, you should be able to get it correctly. So there are multiple options which are correct. You need to decide which of those options are correct over here. Now this ion, depending upon what is the mass number, this ion can hit here. This ion can undergo a circle like this. This ion can undergo a circle like this. This ion can undergo a circle like this. Sometimes this ion can also undergo a circle like this, right? Or maybe this ion can also undergo something like this. When it goes away from here, definitely it crosses away here. It doesn't return back. Okay. See, we have learned all these possibilities. Okay. So the purpose of introducing the previous 2 problems is that to look at all the further possibilities, okay, that are possible over here, and then you look at how to solve this problem. Okay. The value of X for H plus is ion is 4 centimeter, whether it's true or false. Value of X. Okay. Let me assume, what is this X here? X here is for hydrogen atom. What is this here? It is describing a circle like this and hitting over here. What is this one here? It is nothing but your 2 times R over here. It's a 2 times R. So you need to show that 2 times R is equal to 4 centimeter or R equal to 2 centimeter. Have you shown it or not? You already shown it, right? So how do you start with here? Very simple. You need to start with, once again, half mv square is equal to q times v, and then v should be equal to 2 times qv divided by m square root. You get this one here, and after this what you do, you need to get the value of R. Value of R would be equal to mv divided by qb. For hydrogen, this m is nothing but 5/3 into 10 power minus 27. We got this value. So therefore, I am just going to substitute all this value and try to get the answer, which should be 5/3 into 10 to the power of minus 27 multiplied by velocity. What is the velocity? This should be root of 2qv by m. Root of 2qv divided by m, where v is the potential, which is 192. Is your 192 over here. And then m, what is m here? M is nothing but the mass, which is being given over here, divided by q into b. Q is nothing but 1.6 into 10 to the power of minus 27 multiplied by b. What is b over here? 0.1. See, I have taken the same values while I started solving the previous problems. Okay, but only thing is I designed only a part of it. Okay, now we are going into detail. Okay, so when you do this one here, you definitely you get r equal to 2 centimeter, which we have already done this one. You can refer to my, you can go back and see in the video what we have done. Okay, and then so the radius, this area of x is nothing but equal to 2 times r, which should be equal to 4 centimeter. So this part is correct. We already got this. Okay. The next one is value of x for an ion with AM equal to 144. Now, how do we solve this? So for this, what we need to do? We need to solve this equation, which is that equation, this equation, right? R equal to 2 times mu AV divided by QB square. You have to choose this one and finally get the answer. Okay. And we have got this value also earlier. For 144 centimeter, this was 24 centimeter. Sorry, for 144 nuclei, okay, for value of A equal to 144, you got radius to be 24 centimeter. Let us see whether it's the same question. 24, the value of x for AM equal to 144 is 48 centimeter. So he is asking about x over here. What is that we found? We found out the radius. Okay, so let me write it down. Let me go to the next slide. We found out for this one, radius r was seen to be 24 centimeter, and thus you can find out the diameter, that is x is equal to 2 times r, which should be equal to 48 centimeter. So therefore, this is true, this is true. See how nicely we are able to solve JEE advanced problems, right? You are now only a student of IBDP, but you are able to solve it very clearly, right? Okay, for detecting ions with 1 less than or equal to AM is less than or equal to 196, the minimum height x1 minus x0 of the detector is 55 centimeter. Now, x1, what is x1? X1, where is x1 here? X1 should be the maximum distance. Where is x1 here? This is your x1 here. Why do we get this? See, there are some ions, the hydrogen ion, for example, will come and hit here, will come and hit the detector here. So, hydrogen ion has been detected. Now, let us say, for example, if I take oxygen, if I take any other ion whose mass number is not 1, but it is equal to something like around 25. Okay, now what will happen? This ion might come and hit over here. Why does it hit here? Why not it hit here? If you ask this question, that comes from your answer for the formula. What is the formula? The formula is here. 2mv by qb square. You see, r is directly proportional to root a. R is proportional to root a. Let's write it down over here. So we know that the radius here is equal to root of a into r1. See, this is how you should be able to generalize things. Okay, you cannot just keep on referring, going back and so on, but you should be able to, the moment you get that, you should be able to generalize it. These are some of the short keys, something like tips for you. Okay, wherein, so if you want to really get through the advanced course, now what you need to do is, you need to know, like, how do you generalize things, because you need to do it faster. 3 minutes, 3-mark problem, you should not be taking more than 5 minutes. Right? Though I know that the problem is very tough. Okay, every IIT problem would be tougher only, and that's why it's called as an IIT problem. Okay, otherwise it would be called something else. So definitely it has to be tough. If it is not tough, it's a useless problem. It has to be tough. So based on this, now it is equal to root times a times r1. Okay, root of a times r1. What is root a? So if I take this, let us say, for example, as the value of a increases, this r also increases. Okay, and what is this x here? X is nothing but 2 times r. Okay, so x should also increase. For x, for hydrogen ion, this should now be equal to 1 and the r is equal to r1. So this should be equal to 2 times r1. Okay, which is nearby. And for the any other ion, let us say, for example, a very massive ion. What is the massive according to us? The maximum mass could be 196. 196 ion. If I have an ion which is 196 value as the value of A, then this ion should definitely go and hit the last point, at least at least it should be able to hit like this and hit the last point over here, If it goes beyond this value, then it becomes useless, right? So therefore, the height of the detector you need to find. What is x naught? X naught value, where is x naught over here? We found out the value of x naught, which was radius of the hydrogen ion was seen to be 2 centimeter. So x naught, which should now be equal to 2 times the radius of this hydrogen ion when it passes over here. Okay, radius of the path. This should now be the diameter. So this should now be equal to 4 centimeter, right? And similarly, if I take x1 for example, what is x1 here? This is for the 196 nuclei. What was x1? Let me go back and see. For 196, what is the value we have calculated? For 196, we calculated 28 centimeter, right? So we'll take up this. X1 is equal to 28 centimeter, not x1, R196. I'm sorry, R196 was seen to be 28 centimeter. So therefore, if it is a double the radius, that means your x1 should be times 2 times 196, which should be 56 centimeter, right? Now, if I subtract one from the other, what is that I get? Because he is asking you x1 minus x0 directly. X1 minus x0 should be equal to 56 minus 4, which should be 52 centimeter. Okay. Now, what is he asking? For detecting ions with 1 less than AM less than 196, the minimum height of the detector is 55 centimeter. Not necessary. You should have this as equal to 52 centimeter, right? So therefore, this 52 centimeter. Just give me a moment. We made a mistake once again here. See, it falls over here. Then let us say this is your hydrogen ion. This is your hydrogen ion over here, and the x1 is 52 centimeter. So okay, so it says the height of the detector should be 52 centimeter. Now you see, if the height of the detector is 52 centimeter, okay, so it should be shorter enough. But what is being given over here? It says height of the detector is 55 centimeter. So this is false over here. This is false. Okay, then the minimum width of the region of the magnetic field for detecting the ion is 56 centimeter. Now what will happen? So minimum width is asking about minimum width. See, this ion should come like this, should go over here and come over here. Okay, so what is this now? Half circle. If it is half circle, then what should this distance be? This is the width over here. This width is nothing but equal to radius, right? If this is radius, let me just write down the next slide. Oh, next slide is not there. Okay, width is equal to radius. Then this should also be equal to, this should be 2 times radius. 2 times radius, right? So therefore, this should be half of it. This width should be half of this. What is the radius of the 196th ion? The radius of this one was seen to be 56 centimeter. 56 centimeter. So radius is seen to be 20. Just a moment. Yeah, the radius of this is seen to be 28 centimeter. See, if you have this width to be equal to 28 centimeter, that is more than sufficient. Okay, you need not have this to be equal to such a long one, which is 56 centimeter. He is saying that the width should be more than, that's not required over here. Okay, so therefore the minimum width required here is only 28 centimeter, and as a result of it, this is also false. Okay, so we have seen, okay, how to solve such kinds of problems. You know, when you are solving these kinds of problems, what is important is it's not the values but also the interpretation. Okay, so you might get something, but you should be able to decide whether you are doing it correctly or incorrectly and what does it actually reveal. So all this is very, very important. Okay, so with this we come to an end to today's problem, and next problem we'll see it maybe after 2 days later. Thank you for being with me. And if you really like this video, do like, share, and subscribe to my channel so to get more updates. Okay, thank you.